All right, so in this video, we're going to talk about vectors. We'll start geometrically and then move in towards more of an algebraic way to manipulate these vectors. So geometrically, you can see what I have up here on the screen is a vector. We're going to call this point right here A and this point here B. This will now be vector AB. In the text, vectors will be bold, so you can tell that it's a vector and not something else. Because we can't do that by hand very easily, we use the notation AB and then the vector notation on top. Now, the order AB is very important. You can tell this vector with the arrow on the end very clearly has direction to it. So this A, this is called the initial point, and B is called the terminal point. So that's why we have to write it as AB and not BA. So now, vectors have two things, two very, very important characteristics. One of them I've already mentioned. Every vector will have direction. The other component, the other characteristic, will be magnitude. So every vector has magnitude and direction. Magnitude is just the length of the vector. And so that's going to then move us into the first operation that we're going to discuss geometrically, which is scalar multiplication. So I'm going to start here with vector v. Once again, notice the notation. If I want 2v, what I've done now is I've extended my original vector by 2. I've doubled it. Now notice how it points in the same direction, but the magnitude has changed. Let's say I go 1/2 v. Now I'm going to cut in half the original 1/2 v. I'm going to cut in half the original length of my vector v. So something maybe like this. And then finally, how about we do a negative v? So if I take a negative v, now I'm not necessarily lengthening it, but this is where I change the direction. So it'll have the same length as v, but now it's going to point in the opposite direction. So it'll look more like this. Okay, so that's scalar multiplication geometrically. A very, very important thing to remember. Very important thing, and I've mentioned it once, and you can probably see it. And even better now that there's 4 vectors up there. V and kv, where k is a scalar, v is the vector. V and kv are parallel vectors. And again, this is a really important thing to remember. 2 vectors are parallel if they are scalar multiples of one another. Very, very important thing to remember moving forward. So there's some scalar multiplication. I'll go ahead and clear the screen. We'll talk about addition and subtraction. All right, so addition and subtraction of vectors geometrically. So what I have up on the screen are 2 vectors, vector v and vector w. I've got the initial point of v and w connecting right here, and you can see they're obviously pointing out away from each other. We're going to add and subtract these vectors using what's called the parallelogram law. So to find the sum of v and w, what I'm actually going to do is construct a parallelogram. So I'll run this guy over to where this guy intersects, and then the resulting vector right there, that would actually be your v plus w. Okay, so geometrically that's how these vectors can be added. Now addition and subtraction are obviously very easy to work hand in hand because well, as you know, 3 minus 2 is the same thing as 3 plus a negative 2. So now, in order to show you this, I'm going to use a negative v vector. So that's going to be v pointing in the opposite direction. Should have the same length as the original. So that's going to be our negative v. And now, if I construct my parallelogram, the resulting vector this way, that would end up being my w plus my negative v. Okay, so again, that's the same basic idea as I used over here, but now I've used my negative v vector, which we can then take one step further, and I'll just move down here so it's easier to see. This would be w minus v. All right, so Vector addition and subtraction, very, very straightforward using that parallelogram law. Just remembering again, subtraction is just addition of a negative vector in this case. Okay, so now in terms of notation, which will then lead us into the algebraic discussion, vectors are going to be denoted here by some different brackets. Okay, it's not going to be the point brackets, the rounded parenthesis that you're used to, but they're more angled, like greater than and less than symbols almost. So in R2, vector V would have the components V1, V2. In R3, vector V would have the components V1, V2, V3. And you could go into whatever dimension you wanted. You can go to the nth dimension where you'd have V1, V2 all the way up to Vn. But these are the two that we'll stick with for now. So in this component form, our vectors geometrically are in standard position. And standard position means that the initial point is at the origin and the terminal point is at the point V1, V2. So notice the difference in notation here. Again, these are not points because you can see the notation represents vectors, but I've transitioned now to a terminal point V1, V2. Okay? Now, let's talk a little bit about how the algebra works here, and then we'll actually get into taking a look at this all in a little bit more visually. So I'll say vector algebra. If we let V equal V1, V2, and W equal W1, W2, and K is any scalar. Many times in these problems, it's going to be very important to define the vectors that you're going to use. So I've defined vector V to be this, I've defined vector W to be this, and for K to be a scalar. So if we want V plus or minus W, our V, which is V1, V2, plus our W, which is W1 plus W2, is going to equal V1 plus W1, and then V2 plus W2. Now, what I've done here, as you can see, is I simply added the corresponding components, V1, W1, V2, W2. Now, I have said plus or minus here, so subtraction, as we saw geometrically, would work the same way. So I'll go ahead and throw these in here just to convince you that it is, in fact, going to work the same way. All right, so that's vector addition. Just add corresponding components. For scalar multiplication, this one's pretty simple. If we have K times V1, V2, that's just going to be KV1 and then KV2. So we're distributing the scalar through there. A couple things to remember here, and I'm going to make this argument a lot. The first couple sections, it's not going to be obvious, the importance, but it will be as we proceed through the chapter. Whenever you operate on certain things, whenever you do certain things, you're going to get a result. It's very important to understand what that result is. And in this case, you can see we've added or subtracted two vectors, and what we've ended up with is also a vector. So when you add or subtract vectors, you get a vector. With scalar multiplication, you also end up with a vector. Again, might not seem important now, but I promise you these types of things are going to be really important to think about as we move forward. So adding and subtracting, it leaves us with a vector as well as scalar multiplication.